Hello. In this unit, we're finally going to do attention and the transformer. And we're going to do that in the context or while studying language modeling. I'm going to skip over recurrent neural networks because that's something that was very popular in the middle of the last decade and is not used much anymore. So we're going to do language modeling and attention and the transformer. Okay, so language modeling. So language modeling is computing the probability distribution over language. So the idea is that every sentence of English or every document, every newspaper article has a probability that we can compute basically by computing the probability of the next word as we go along through the document. And here I've written the fundamental equation of deep learning. This is the cross entropy loss. And we're trying to find a model. And today we'll talk about the transformer language model, large language models. We're trying to find the parameters of a large language model. And we do that first by training a foundation model and then fine-tuning it with instruction fine-tuning and so on. That's the very modern methodology for large language models. But we start with a foundation model and we train that foundation model by next word prediction. So how is that related to this very general fundamental equation of deep learning? So here I'm drawing text, some article or some web page from some hypothetical population of possible texts. And I'm going to try to find the model parameters, the trillion weights, in GPT-4. I'm going to try to find those trillion weights by minimizing the expectation or the average over drawing a text from the population of minus log the probability of that text. And here I'm assuming that all the texts have the same length. Really, this is really going to be a next word loss that we're interested in. So it's going to be independent of the length of the text. But intuitively, we're saying, I'm going to take the average over a block of text. Let's say we fix the block length to be 1,000 words or 1,000 tokens. We'll talk about that in a minute. I fix the block length. So I draw a block of text and I compute the negative log probability of that block of text. So training the base model of a large language model, the foundation model, is using the very same universal fundamental equation as image classification, as any other problem in deep learning. So language modeling. So let's say a little bit more formally about language modeling. So we're going to let V be some vocabulary. The simple way to think about this is V is the set of words of some language, a vocabulary of words. However, in modern systems, it's very difficult to define words, for example, to cover all possible names or to include names from foreign languages. So instead of words, people talk about tokens. And a token can be a fragment of a word, just 3 or 4 characters. And by using subword tokens, we can represent any block of text as a sequence of tokens where the number of tokens is fairly limited, like 50,000. 50,000 is small, manageable. So a modern language model would have 50,000, be using 50,000 tokens. Tokens, however, typically do not cross word boundaries. So we have subword tokens, but a word would be a sequence of tokens. We don't let a single token cover more than one word. And we are interested in the probability distribution over the strings of tokens. Now here, I'm going to sort of think about sentences. So we're letting populations be a probability distribution we're assuming some population probability distribution over sequences of tokens. We want to compute a probability for a given sequence of tokens. And this is our fundamental equation. And note that this probability is exponentially small, right? If the probability of each token was a half, then if I've got n tokens, I've got the probability becomes 1 over 2 to the n. So probabilities become exponentially small. But the negative log of the probability, is manageable, grows linearly in the number of tokens, because the probability is a product and the log of a product is a sum. So this negative log probability is growing linear in the length of the block. Okay, so we're going to use autoregressive models. What does that mean? It means that the probability of a sequence of tokens is being modeled as a product of conditional probabilities. So the probability of token 0 to token t is the product of the probability of each token being generated given the previous tokens. So it's the product over all times in this sequence of the probability of that word or that token at that time given the preceding tokens. And any probability distribution over sequences defines some conditional probability of this form. So in principle, this autoregressive probability model can model any distribution over the sequence. And that's important, right? Because in language, this distribution can be incredibly complicated. And this conditional distribution is being modeled with an incredibly complicated model, 100 trillion parameters. And in the limit of arbitrarily sophisticated, arbitrarily expressive models, this sequential autoregressive probability distribution should model the distribution over the whole block. Now it's called autoregressive because this is viewed as a regression problem. It's regressing the next word or the next token on the previous tokens, but then it's feeding that token back into the sequence and regressively predicting the next one. So it's an auto-regression. And that word, auto-regressive model, is general and important to remember. It means you take a structured value in general and predict one piece of it at a time. And there are autoregressive image models where you're predicting each individual pixel one at a time, given the precedingly or previously selected pixel. So the word autoregressive is general. It means you're predicting one piece at a time. In a language model, you're predicting one word at a time, or one token at a time. In language modeling, people will often think in terms of sentences, and a sentence has an end of sentence token. This is not used much in modern training, model learning. Model learning will simply take a block of, say, 1,000 tokens, independent of where the sentence is at, and do a prediction over that block. But if you're thinking about sentences, you introduce an end of sentence, EOS, end of sentence token, to terminate a sequence. So if we take the negative log probability of this sum, then that's equal of this product. Take the negative log probability of this product. That's equal to a sum of a negative log probability of the next word given the previous words. So we're summing together the loss at each word. Now, another thing that's nice about autoregressive models is if you have if this space is small, the space of tokens, and 50,000 tokens is small. If this space is small, then you can actually calculate the probability distribution explicitly, compute a probability for each of the 50,000 tokens, and then you can sample from that. And when you sample from that, you're sampling from your probability model over the sequence. So an auto-regressive model can both model the probability and it supports sampling from the model's probability. And that is what is done in language generation. You're sampling from the probability distribution of the model. Okay, word embeddings. This is a fundamental aspect of language modeling. The idea is that for each word, or actually for each token, you have a vector called the embedding of that token. And that vector is representing in some way the semantics of the word or the token. Typically, words are individual tokens. So you have word tokens and then you have subword token units. We're going to assign each token a vector, which is its meaning. So the vector is representing the meaning of each word. And this is typically represented by a matrix. So in matrix notation, you would say the embedding of a word is a tensor with some index over the different features in that vector. I always think of this as simply a word or a token having an embedding, which is a vector. All right. I'm going to skip over this section. I have spent a lot of time in previous versions of this class, matter of fact, just the most recent one, in explaining recurrent neural networks, but I'm going to skip it. It's not used much anymore. There are variants of the transformer that are described as recurrent neural networks, but you can understand those variants without going through the old school version of recurrent neural networks. But I do want to start by talking about machine translation. So this was one of the really fundamental papers in deep learning, was a paper on machine translation by Ilya Sutskever before transformers and independent of attention and translation. And he has a great quote. He had a very simple model, and he said, minimal innovation for maximal effect. And I love that quote. But let's consider the problem of machine translation. So I've got some English coming in, and I've got some Japanese coming out. And in the original paper, it was French, English to French, or French to English. In the original paper, in Ilya Sutskever's original paper, there was an RNN that computed a thought vector for the input sentence. And then this thought vector was translated back into the output language. So that you had a thought vector for the English thought. You took the thought vector for the English thought and you generated a French version of that thought from the thought vector. And it was amazing, astonishing that this worked at all. Did not work well, but it worked much better than it had any right to. If we look at the fundamental equation of deep learning, what this translation problem amounts to is a conditional probability. I want to compute the probability of the French given the English. So it's the conditional version of the fundamental equation. Given the input, I want the model to minimize the negative log probability of the output. Minimize the negative log probability of the output given the input. It's just like saying minimize the negative log probability of an image label given the image. This is like a labeling problem. I'm labeling the input sentence with an output sentence. So the mathematics is still the fundamental equation. It's the conditional version of the fundamental equation. So that's just what this slide is saying. We're interested in the probability of the output given the input. And our objective is to minimize the cross entropy of drawing XY pairs from the population. In this case, X and Y are sentences, input sentence, output sentence, I want to find the model parameters that in a translation system that minimize the average value of the negative log probability of the output given the input. All right, let's skip to this, the introduction of attention. So this paper appeared almost simultaneously with Ilya Sutskever's paper. This is not yet the transformer. It's still 3 years before the transformer, but this is what introduced attention. And the idea here was that as you're generating output in a translation system, intuitively, each position in the output, each word in the output often corresponds to a particular word in the input. So as you're generating output, you should be paying attention to particular places in the input. So the idea is that there's a correspondence between where you're generating in the output and where you should be looking at in the input. And this alignment problem is addressed by attention. So in this system, we're attending to different places in the input based on where we are in the output. And I'm going to sort of skip over the details of this, but it's worth pointing out that before the transformer, now we're talking 2015, almost 10 years ago, but before the transformer, there's another translation problem, which involves images. So in image captioning, given an image, we want to write the caption for an image. We can think of this as an input-output pair. So we're given an image and we're outputting a sentence. So this is we're minimizing the log probability of the output sentence, the caption, given the image. And using this methodology that was introduced for translation, as we're generating the output, we're paying attention to different places in the input. And as we generate the word frisbee, we can look in the image and see where the model is attending to as it's generating frisbee. And so this was kind of interesting because it was showing that as this model, which is just trained, all it's trained on is with a general attention mechanism, maximize the probability of a given caption, given the image. What you observe is as it's generating the word frisbee, it's, quote, looking at, its attention mechanism is emphasizing the frisbee. And in this example, as it's generating the sentence word, the model is looking at, as it's generating the word girl, the model is paying attention to the part of the image that contains the girl. So this was, again, this was very interesting at the time. All right, here's the transformer. 2017. Transformer, attention is all you need. Laswani et al., 2017. All right. So in the transformer is based on attention. And there are different forms of the transformer. One is called an encoder-decoder transformer, and one is called a decoder-only transformer. But in all cases, what we've got is a sequence of words, and we're going to compute a stack, a residual stack of vectors at each word or token. Okay, so there's this notion of the residual stack. There's an input tensor. What is this input tensor? The input is a sequence of words, a sequence of tokens. So this has a vector at every input position. I'm using T in to mean a position in the input sentence. So at every position in the input sentence, I've got an input vector, H0 in. Sorry, these slides were written for the translation problem. Let me skip ahead. Oh, let's stay here. Apologies. All right. So we've got a residual stack. The residual stack has a vector at each token. And for each token, T in, we're going to have the input layer and then later layers. And each one of these later layers is computed with a residual connection involving a computation and a residual path around that computation. So it's just like ResNet. So we just did ResNet. This is also a residual stack with with computation layers with residual connections, sums going around the computational layers, just like ResNet. Each layer is a vector at each position in the input sequence. So I'm going to skip to the next slide. Well, I might come back to that. Okay, so here's the residual stack. So we've got words. We've got a self-attention layer. We've got an add and normalize layer. So this is a residual connection. This self-attention is taking a sequence of input vectors, a vector at each token. It's doing a self-attention operation. I'll talk about what that is. Intuitively, each position is attending to each other position. That's the self-attention. So it's attending to itself. That self-attention layer uses that self-attention to compute a next layer. The next layer has a vector at every position in the sentence or in the sequence of tokens. So I'm going to add these. This is just a residual connection. I take the input layer, I add it to the output of this layer, and then I follow that with a normalization layer, a layer normalization. So this adds and normalizes. Then I take each position in this sentence or sequence of tokens, and I pass it through a feed forward, independently pass it through a feed forward layer. So this is taking the vector at each position, and this actually does a bottleneck step. It takes that position and increases, it takes that position and transforms the number of neurons to an intermediate number of neurons. This is like the bottleneck layer in ResNet, except this time it's going to a larger number of neurons. So it takes at each vector, at each position, the vector is transformed to a larger number of neurons. Then you do a multi-layer, then you do a fully connected layer. You do a fully connected layer at each position. It's not a convolution layer, it's just a fully connected layer. And then you reduce the dimension back down with another linear layer. And then you do another add and normalize. And this is the residual block that's just repeated some number of times. And this defines the residual stack. Okay. Note that this computation, if we think about how long this computation takes, all of this is, everything runs in parallel. The attention runs in parallel. It takes a lot of space because it's attending to itself, but the time requirement is just linear in the depth, right? Since everything is being done in parallel, independent of the length of the sentence and independent of the size of the vectors, this is basically taking time proportional to the depth. So it's very fast in training. And this is different from recurrent neural networks, which had to compute serially in the length of the sentence. So one big advantage of transformers is just their speed in parallel on a big enough GPU. In that sense, it's more similar to a convolutional neural network, which is also very fast. Its time is just proportional to the depth of the network, independent of the image dimension. So self-attention, that's basically what I've been talking about, is self-attention. Okay, transformer heads. So I haven't fully explained the nature of the self-attention layer. So the self-attention layer has this concept called a head. So there's actually many different self-attentions taking place. Each head computes an attention between the different positions in the sentence. So we have a position T1, and that position is defining an attention over all the other positions. And that attention is basically a probability distribution. It's normalized. It's a convex combination of the other attention, of the other positions. And that attention, there are different attentions being computed at each layer. All right, let me try to say that again. So we have heads. Don't worry about what a head is, except that each head is computing a different attention. What is an attention? An attention, a self-attention. What is a self-attention? A self-attention takes a position in the sequence and computes a probability distribution over all the other positions, possibly including itself, over all the positions in the sequence. And one way to think about this is that the head might correspond to a syntactic relation. So if I've got a verb in the sentence, I might want to know where is its subject. And I might want to know where is its object. Like if, Mary saw John, who, there's the verb saw, as in, she switched on the light so she could see John. Mary saw John. There's the verb saw. That verb has a subject, Mary, and an object, John. So I might have a head that at the word saw is trying to find the subject of the verb. And a different head that at the word saw is trying to find the object of the verb. So we don't really know what these heads mean. People have found heads that look for grammatical relationships, but you can think of it as the head as defining a particular kind of relationship between positions in the sentence. And since there are different possible relationships, you want different possible heads. So you have a head K, and the heads are just trained. There's no semantics built in. The model just has many heads, and the heads learn to provide information like subject or object through the training. So abstractly, there's just an abstract head. So how is this attention computed? So there's a network. So these are going to be matrices, model parameters that are specific to a particular head. So K is going to be a head. And we're going to compute at this position for this head is one position T, and I is an index on the neuron, on the feature, right? So we're going to compute for a head and a position and a neuron a value. Or another way of saying that is for a head and a position, we're going to compute a vector of neuron values. And that vector of neuron values is computed by applying a certain matrix to a query matrix to the vector at that position. So I've got a position that I want to compute a self-attention on. I take the query matrix and I apply it to the vector, and that gives me a vector called the query. The query is a query matrix applied to a query matrix with these parameters applied to the vector at that position. I also compute in the same way a key. So at each position in the sequence, I'm computing by a matrix application, a query and a key. And then I compute an attention from each position to each other position. And each position is going to attend to each other position under the relationship defined by this head. And that attention is computed with a softmax over this other position. The softmax is guaranteed to produce a convex combination over this other position. The softmax of a constant that depends on the size of this dimension, one of the square root of that dimension. That's related to k to weight initialization. Involves a one over a square root of a dimension. Ignore this. Okay, so the attention is a softmax. The attention from T1 to T2 is a softmax over T2, giving us a convex combination over T2 of the query at T1 and the key at T2. You take the inner product of the query at T1 and the key at T2, and you take the softmax of that inner product to get the attention. And there's a different attention for each head. Each head is representing a different relationship between the tokens in the sentence. Okay, once I have that attention, each position also has a value. And that value is also computed by a matrix times the vector. And then what I do is, given the attention, I take this attention as a convex combination, and I compute the convex combination. This is like a weighting now. This H tilde for this head at this position is a convex combination of the value at the other positions for that head. And the value is head specific. The value is computed at a position by applying a matrix to the vector at that position, where the matrix is specific to the head. So all these matrices are specific to the head, the particular relationship between words in the sentence. Okay, so let me try to say that again. At each position, I get an attention, a convex combination across the other positions. At the other positions, I have values. I weight the values by that convex combination, and then that gives me a value for that head at the new position. And then what I do, I have all these heads, right? I have capital K different heads. I concatenate them all. And then I take that this big concatenated vector, which is now just all of these vectors I get from the individual heads. And I apply a matrix to that to get the next layer at position T. So that is the self-attention layer. It's a complicated beast. So we've now defined the self-attention layer. This is just the add and normalize. This is the feed forward. And that now we've defined the entire transformer. Now there are some things I haven't mentioned. I'm going to skip over the feed forward layers. So that's the end. There's some things I haven't mentioned. And that is, I talked about encoder-decoder models. An encoder-decoder model is used in machine translation. So the encoder and the decoder are both transformers. But if you want to do, if you want to compute a probability, you have to be auto-regressive. In order to train these things based on next word prediction, you can't be looking into the future when you predict the next word. So to prevent the system from looking into the future when it predicts the next word, you use something called causal masking, meaning when you compute the vector, the value vector at every position, you force the attention to only be attention over the preceding word tokens in the sequence. So no vector is looking into the future. So that means that the very first vector is computed just from the very first input. The second vector is computed from the first input and from the entire first stack and the second input, and so on. And that is what that, but it's all done in parallel, right? It's still all done in parallel. It's just the causal masking is forcing things to only look into the past. So there's no sense in which you're really generating one word at a time. You're always generating everything all at once. It's just that each word is only looking at its past. Okay, that's the transformer. That's a pretty challenging unit. But I'll stop there and thank you for listening.